Now that you've learnt about spy communication, let's take a look at another popular form of serial communication known as I2C. I2C stands for Inter-Integrated Circuit and is widely used for serial communication between devices. It's slower than SPI but has the advantage of requiring only 2 pins for communication, clock and data. It allows for multiple master devices on a single bus, and rather than hardware lines for accessing slave devices, each device on a bus has a unique address, usually 7 bits, which is transferred along the data line to select the appropriate device. Because I2C shares the data line for both transmitting and receiving data, it is known as a half-duplex protocol, as data can be transmitted and received, but not at the same time. The I2C communication protocol is slightly more complicated than SPI due to the extra layer of protocol required for the shared data line, and it is also slower than SPI. However, the ability to control hundreds of devices using only 2 lines is quite advantageous in many situations. Like the previous section, I've included some diagrams of the communication structure for the I2C data. However, the library will be taking care of most of the heavy lifting for us. Read and write bits are sent along with the data to determine whether the master wishes to read or write information, with an expected acknowledge bit, or ACK for short, to determine whether the byte was successfully received by the other device or not. We can control an I2C device from an Arduino using the wire library, which makes I2C communication incredibly straightforward. Like SPI, it is possible to emulate the communication using software functions. However, again, this leads to some burdensome software overheads. So if you're using I2C, ensure that your chip has a hardware I2C port. For the first I2C example, I'll be connecting 2 Arduino boards up to exchange data via the bus and print it out on the serial monitor. It allows us to use the wire library directly and get an understanding of the control sequence. After that, we'll connect up a real-time clock module via I2C and use a specific RTC library to control it, which handles the I2C communication behind the scenes. So connect up your Arduino boards as shown in the wiring diagram in the workshop page, and we'll run through the code. Alrighty, so here I've got loaded up the master reader code. Now there's 2 sections of code that are important for this example because we're using 2 Arduino boards. So if you go to the workshop page, you can see that I've got the source code for the master reader Arduino demo, and this is taken from the Arduino reference site because it's such a good example of demonstrating their wire library. And then we've got the slave sender Arduino code. And what that means is that the master is going to request some data from the slave will send it, and the master will then print that data out to the serial monitor so we can see what's going on. So take the master reader code into your Arduino, and now we're going to upload that to one of our boards. Now you'll notice I've got the 5-volt line connected between the Arduino here, and that's just because I'm only using one USB cable, which means I need to get data across to them. And you can use this 5-volt line to power another Arduino only if you are sure that it is a clean, regulated 5 volts, isn't unlikely to spike. Given it's coming from the other Arduinos regulated directly, it's a pretty safe bet that it's going to be usable. So I'm just using that to allow us to run 2 Arduino boards with only one USB cable. However, you can use 2 USB cables as well. That's perfectly fine. So take your cable and move this across here so you can get a better view. There we go. All right. And so I've connected that up, and this one's going to be my master reader. So I'm going to select the appropriate COM port for that guy. Hit upload, and while that's uploading, I'll grab the slave sender code here. All right, so that's successfully uploaded. Now we'll copy the slave sender in here, and I'll go through the code line by line in a moment, and we'll take a look at how it works. Now I'll connect the USB port up to this guy, and you can see that when I connect that one up, that the lights on this one turn on as well because it's sharing that 5-volt line. Select our new COM port, upload that. So to make a bit more sense of it, I'll go to the workshop page where you can see the code against each other. So the master reader is quite simple. We're including the wire.h library. Then in our setup, we're initializing the wire library much in the same way that we had to initialize the SPI library. We use wire.begin. Then if you're the slave device, in the brackets there, you would put your address. So serial.begin, initializing the serial interface. Then here we're using wire.requestFrom. and we're requesting some data from address number 8 on the bus, and we're requesting 6 bytes of data. Then it waits, and while there is wire.available, so similar to the serial.available, it says if there's data available from the I2C incoming data, then let's read that sequentially, get each character that's coming in and print it out to the serial terminal. So that's the master section there. Now for the slave, there's a little bit more to it. We've got the wire library again. Now we're initializing the wire library, so the I2C interface with address number 8, and then we are creating a handling function here. So wire.onRequest request event. And what this does is it creates a separate function which can be accessed whenever the on request is sent. So request event, so a function that executes whenever data is requested by the master. And so whenever our master says, hey, slave, I want some data, it will run this function. And it says wire.write hello. So it pushes the characters or the actual letters themselves, HELLO, along the I2C bus to the master. And that is how both of these are going to work. So I'm going to take the USB cable and plug it back into my master device so that I can read from the terminal. And now if I select the right COM port, go to serial monitor, I can see hello is being transferred every, what's the delay time on that? Every second. So if we change that, this is the slave device actually, so I'd have to replug it in. So I'll leave it as is, but you can see that it's transferring hello over and over again because that is the data that our slave is trying to send. So now that we've looked at a basic I2C example, let's look at using it for something a little more practical. For this example, I'll be interfacing an Arduino with an I2C real-time clock module, or RTC, which allows an Arduino or other board to get an accurate timestamp regardless of whether or not power has been disconnected, thanks to the coin cell battery on the RTC, which powers the module after power off. The easiest way to use the RTC module is it's an Adafruit module, so we're going to use Adafruit's library for it, which I've included a link to in the section resources. Again, take a look at the wiring diagram in the section resources and we'll dive into the code, which is an example that we're borrowing from the Adafruit library. Alrighty, so I've got my breadboard all set up and it's quite simple with I2C only requiring two lines, the data and clock. Clock being on the furthermost pin and data just inside it, and then of course power and ground. So let's take a look at the code for that one. Go here. Now, as I mentioned, this is an Adafruit branded module, which is fantastic. It's outside of the SparkFun Inventors kit that we've been using, but it's such a valuable module, and Adafruit have fantastic software resources and support available for it that it seemed a shame not to use their example. So let's take a look. At the very top, we can see the include wire.h, and then we're including the RTC library. Now, we don't have the RTC library, so we need to go and download it, and we'll look at a more practical real-world example of downloading a library and including in our Arduino IDE. So in the section resources, here, it'll take us to the Adafruit tutorial page for this particular module, and we can download the RTC library. Alright, now after extracting that, actually we can just include that directly as a zip file. Include library, .zip library. I'll go to downloads. I can see that guy there. So we include that, and it will now include the RTC library in our sketch, which is fantastic. Then we're saying the type of chip on board the RTC module that we're going to be using, which is a DS3231 chip that we've got there. Then we're creating a character array. Now this is actually a special type of array known as a two-dimensional array. And you can see that unlike a standard array, we've got two sets of indexing here. Now what this says, it's a two-dimensional array, so you think about the fact that it has one dimension that way and one dimension that way, or in other words, you can reference both a line or a row and a column. So the maximum number of individual elements that we're going to have is 7 because there's 7 days of the week. then the maximum number of letters that is in any one of these words is 12. So we use the maximum there so that each word has enough space. And then, so if we were to reference days of the week as 0, 1, then we would go to element 0 and it would go to 1, or the second part or the second letter of that particular element, which would be a U, which is really cool. So that is how we can use two-dimensional arrays. And it just creates a day of the week that we can refer to. And it just has some references in case you're using a special type of chip, the ESP8266, which we are not. So if it doesn't do that, then it just initializes the serial port, waits for 3 seconds, waits for the console to open, and then it checks to see if there is an RTC on there. So if it can't begin the RTC function, if it returns not true, then it says, hang on, we can't find an RTC, you need to connect it up. Then if it's lost power, then it will go through the calibration process and it will print out, after that it will print out the correct time, date and year according to the serial print structure that we have here. Then it waits for 3 seconds and prints it out again, which is really, really cool. So we'll go ahead and upload that to our board. Make sure we've got the correct board selected. Now it'll go through and compile, and it will base the time that it uses for calibration off the Arduino IDE. So in a moment it's going to print out to our serial monitor. I'll full screen that so you can see. Alrighty, so as you can see, it's not giving us the correct date, obviously because it hasn't had a chance to calibrate itself. But we can see here that it is working perfectly once it's given a second, once it's initialized. And now we're getting the time. So 1600 hours, which is 24 hours speak for 4 o'clock in the afternoon, which it is. And it is the 9th of the 3rd, 2017, or backwards if you're one of our American friends. And just like that, it will keep our time up to date, which is really, really cool. And if we exit this, if we power off, just to show you this isn't some sort of Arduino trickery, power that off, connect it back up, and open our serial monitor up again, it will keep that time, which is really, really cool. So it should show that it's 4:01. Indeed it does. That's the part that we're looking for. All right, fantastic. So that is the real-time clock module, and it's really, really easy to use. In fact, it's so easy because Adafruit have created such a fantastic library and some really good examples. So you can take that same concept where all it's doing is saying date time now is equal to RTC now. And RTC now is a function of the RTC library, which grabs the current date and time and prints it out. And you can use that for whatever you want. It's extremely accurate. And this module is actually really, really cool, especially because it has an onboard crystal on the chip, which makes it so chunky. Now, the crystal's timing, or the oscillation, which keeps the clock running, can deviate slightly according to the temperature. Now, inside this, it has an internal temperature sensor, which can detect the temperature and use a scaling function to actually adjust the clock on the fly. So it's extremely accurate, which is really, really cool. I love using this module for real-time projects, and that is all about the I2C interface.